So I'm going to be going quick through when you have a given moment and you're doing here elastic stress analysis. Elastic stress analysis means distribution of the stress is going to look like this. The plastic is going to look like this. Plastic means the entire steel is going to be under Fy, F sub y, whether you have it in tension or you have it in compression. So in this case, if I assume here plastic neutral axis to be at this location, this entire section is going to be under F sub y here for the steel, 0.85 F prime C, and also in tension is going to be F sub y. But the elastic is going to be completely different. It's going to be based on the amount of strain and based on the given moment on the section. And this moment will include dead load and live load. If you are doing here elastic stress analysis, the stress due to here bending is going to be equal to the moment times the distance away from the CG of the section, the centroid, divided by the moment of inertia. And this can be above or below the neutral axis. And we understand that this here composite material, which means that we have here steel, we have concrete. So we're going to have an issue here, which moment of inertia that we need to work with. Is it going to be based on concrete? Do we assume that the entire section is going to be concrete or steel? The very common analogy and analysis that we see here when you consider the whole thing made out of steel. Now, how would you convert the concrete into steel? The way you do it, you divide the concrete width by the N, the modular ratio, and N is equal to, it's going to be ES divided by EC. Range usually goes between 6, let's say, to about 9. In some cases, a little bit higher. Here is the N, the modular ratio, and we're going to have an example that we go through it. So I'm going to jump here to the example. This is the one that we went through already, and then we said that we are going to be doing it with two different assumptions. So here's what happened. Total width of the concrete flange was given at 87 inches. We're going to be considered only to be 10.88. The reason because we're going to be taking this width divided by N, which is 8 in this case. So please, when you have 8.4 or 8.6, don't round it up to 9, and instead just make it 8. Any number above 8, you're going to be cutting off this fraction and just keep it as 8. Here's the width again, 87 divided by 8 is going to be 10.88 inches. Now, someone's going to say, why don't I take the 5-inch and divide it by N instead of taking the width and divide by N? Because what you're doing here, you're taking the area, convert it into steel elements or steel area. If you take here the 5-inch divided by 8, what's happening, you're going to be pushing the height of the concrete to be very small here. And if you keep the big width and reduce the thickness, moment of inertia is going to be much higher. So because the moment of inertia that you're taking here is going to be about the x axis. So the right way of doing it is when you divide the width so that you keep all elements or like area elements to be at the same distance away from the neutral axis or the plastic neutral axis, if you like. So if you're doing here elastic stress analysis, you keep it away from the neutral axis, the elastic one, which is based on the centroid. If you're doing here plastic analysis, you keep it at the same distance from the plastic neutral axis. So let's say for now we're working here with elastic stress analysis, so we're going to keep it at the same distance away from the centroid of the section. Now, if you start here to reduce the depth or the slab thickness and divide by N, it means that you're changing here the distance from the centroid to each area element. But if you divide the width, you're going to keep each area element at the same distance away from the neutral axis. Now, after this, yes, go ahead.
Professor, just a really quick question. For the N value, you said we always round down, even if it's like number 0.8 or 0.7, we always round down?
Yes, so let's say that this number after a round analysis turned to be 8.8. What number would you consider in this case?
8?
Exactly, yeah, you're absolutely correct. So you're going to be cutting it down.
Okay, thank you.
Top of this fraction, just take it out and use this 8.
Okay, thank you.
No problem. Now, after we convert this section into steel area elements, I need to find out the moment of inertia. Now, if you do this moment of inertia in this case, the E that you need to use, the modulus elasticity, is going to be the 29,000 because now you convert or transfer the concrete into steel area element. As it says here, here's the area of the concrete based on 10.88 times 5. This is going to be the area of the steel section, total area. Y is going to be the distance from top of the section to the centroid of each one of the subsections. So for example, concrete here is going to be 5-inch. Rectangular section. The distance is going to be 2.5 inch from the centroid of this section to the top, 2.5 inch. Total 0.95. Now where is this coming from? This is coming from the centroid of the steel section, which means 1/2 of 15.9 plus 5 inch. Now you do A times Y, take this total moment of each one of the sub areas about the top of the section, divide by the total area 65. With that you get the centroid location. Now centroid location, that was kind of general layout that I expect for the section. Now what happened when this becomes here 4.2, I find out that this centroid or this neutral axis, it is happening right here. Because at this sense, this Y bar turned to be 4.2 instead of 5 inches. It means that this little section of the slab, which is between the neutral axis and between the top of the steel beam, is going to be falling under tension. Here's the reason again. Anything above the neutral axis is going to be in compression, anything below the neutral axis is going to be in tension. Now you put a fraction here or a little piece, this partial area of the concrete, to be in tension. And we understand that concrete is not good in tension. So what should we do? If you feel that this little distance, which is 0.8 of an inch, is very small and you can ignore it, go ahead and ignore it. If you like to consider it, it means that you're going to be redoing this work here, considering that this, the depth of the neutral axis from the top is going to be like one of these unknowns. And you may have an equation from the second degree in this case. We're going to be going through this. So at the beginning, we decided that we're going to ignore this little bit of tension section of the concrete. Just ignore it for now. So what's going to happen? Here's the amount of inertia for that section, considering neutral axis to be right here, and considering that concrete is going to be okay in tension, which means concrete now is going to be able to take some tension or tensile stresses. Just an assumption. After that, since we're interested in the stress, top of the concrete, top of the steel section, bottom of the steel section. So I need to find out, if I'm going to go back here a few slides, to find out the term C or Y, if you like. I'm going back here to this equation. This C. C is going to be the distance from the neutral axis measured from the centroid of the section, the global section, or the composite section, to each point that you're interested in find the stresses at. So for example, at one point, your C value is going to be location from neutral axis to the top of the concrete. If you are interested in stress on top of the concrete, your C distance, this is why it's called here Y top, if you like, is going to be from here to there. If you're interested in the stresses right here, top of the steel, it's going to be the distance from here to there, which is a 0.8. So this distance 4.2 is going to be your C value if you're trying to find out the stress at the top of the concrete. So okay, from here to there, it's going to be 4.2. If you're trying to find the stresses here at top of the steel, it's going to be roughly 0.2. Excuse me, 0.8. If this 4.2, this is going to be 0.8 of an inch. If you're interested in finding out the stress at the bottom of the steel, it's going to be 15.9 plus the 0.8. And this is exactly what I have here. Okay. So here's the equation. Is going to be the stress at any point is going to be equal to the moment, and the applied moment is equal to 160 cubic foot multiplied by 12 to convert it into inches. It's going to be cubic inch divided by the moment of inertia. Now, which moment of inertia? We're going to say transpose or transferred moment of inertia. This is going to be the moment of inertia, assuming that we have steel only. So I'm going to be looking at this equation here. It says N. This equation does not include an N. This equation does not include an N. So if you like to assume that the entire section here is going to be made out of steel, do not show this N in your analysis. So I'm going to say, let me look here at the bottom one, because it is already steel and there is no discussion about this. Here's the moment, 160 times 12, divided by 1530. This 1530 is going to be the moment of inertia, transferred moment of inertia, considering that the entire section is made out of steel. Multiply by 16.7. Now 16.7 is going to be the distance from the neutral axis, the 0.8 inch, plus 15.9. Distance from this red center line all the way to the bottom of the steel section. And with that, I have a stress of 21 psi. Now the stress in the steel at the top of the steel beam is going to be equal to how much? Now let's consider it to be steel. It is, yeah, it's true, it's steel. So it's going to be the same moment times the 0.8 of an inch, roughly 0.8, which means the distance from the neutral axis going down, this is going to be 0.8 divided by 1530. Now this is going to be the stress in the steel, not the stress in the concrete above the steel. Now, if you wanted to find out the stress at any concrete location here, at any concrete element, so in this case, you need to divide this by N. Why? Because you need to bring it back into concrete element. Otherwise, the stress is going to be just overestimated. It's going to be multiplied by N. So in this case, what you need to do is to do the same equation, but in this case, you divide by N. Same moment times 4.2 distance from the neutral axis to top of concrete, divided by 1530, moment of inertia, again divide by 8. Now you got here 0.66 psi. Now I need your help here with me to tell me how much is the stress right on the top of the steel beam in the concrete section, not in the steel section. What should I do to this number to determine the stress in the concrete right here above this element? So I'm going to be zooming in. What I'm trying to do is to find out the stress right here.
Should you divide it by A?
Divide what?
ST by FST by
Which means
A?
this one, almost 1.
Yes, question mark?
Yeah, so what number do you get? I mean, I'd like to see here, what number would I get here for the stress in the concrete?
It's 0.124.
Let's say 0.124, 0.125. This is going to be a very good value. Yeah, it's going to be 0.124. So let me put it here. So I'm going to say the stress in this location is going to be 0.0124 KSI. It's going to be the stress on the concrete, right at the interface. So here's a question to you. Do you think that the concrete is going to be cracking at this tension value? Just a question here for you guys. I know that you have guys, you have taken concrete 408, and in concrete 408, you have the cracking moment and the cracking stress. What is the stress at which the concrete is going to start to crack? Anyone can give me an idea? Is there an equation for it?
Is that the 0.75 square root
Yes.
of F prime?
7.5, not 0.75, 7.5 square root of F prime C, right? So I'm going to say this symbol here to 1/2, correct? Or 2.5. How much is this? Can someone help me here with this? In our example here, what was the concrete strength F prime C? 4 KSI. Now in this equation here, do you need to use 4,000 or 4 KSI? How much is the stress limit here for cracking? Need your help. So let me put equals
474 PSI.
474 what? What unit?
PSI.
PSI. Good. So in order for the concrete to crack, right, it needs to be at 474 PSI at this location. Now, how much is the stress in the concrete at this location? So we're going to be looking here. It's going to be equal to 124 PSI. So is the concrete cracking at the interface between the steel and concrete?
No.
No, it is not cracking. It is not yet at the 474 psi limit. So someone can say, concrete here is good. I don't see here any problem to consider that this concrete is going to be working in tension, because the stress level is going to be 124, which is very low compared to the 474, the cracking stress in concrete. So in this case, I'm going to say, yeah, you are absolutely correct. Another opinion would say, whenever concrete is going to be in tension, if you're doing here a design case, you should ignore the concrete tensile stress completely, which means in this case, there's no tension here. You cannot have tension in concrete. So it depends on the type of analysis that you're doing. If you are doing this analysis, let's say for research, you're going to be doing this. You're going to say, I would let the concrete here to be able to take some tension. If you are doing it for design purposes, in this case, you say, I'm going to be ignoring this little piece of concrete. Are we good? Any questions?
Doctor, how did we get the 0.124 again? I know we divided the 0.998 by 8,
The
but I'm not sure why.
Yeah. How much did you get when you divide this by 8? Is it 124 or 125?
It's 0.125, but
Okay.
like I'm curious why we divided by 8.
Divide by 8. Okay, let me change this to 125 since it's going to be very close. So I'm going to say 125 psi is acceptable. It's not going to change our concept here, but this is a very good question. Why do we divide this by 8? So we need to go back to this equation. We need to understand it. This equation is okay to use it if you have a homogeneous section, which means the entire section made out of one material. This transferred section, we consider that it's going to be made out of steel. You agree with me, Mike?
Yes.
We say that this is now the whole section is made out of steel. And this moment of inertia assumes that the entire section made out of steel. So when I find out the stress at any location here, and if I like to use this equation here, it's going to be based on this assumption that the section is made out of steel. But reality, once you get to this little piece, this is going to be made out of concrete. Now you'd like to bring it back to the fact that it is made out of concrete, and the stress here is kind of overestimated, right? So you need to bring it back to the original value of the stress in concrete. This is why you need to divide it by N, which is the modular ratio between ES to E sub C.
Oh, okay, that makes sense.
Okay.
Thank you.
Great, no problem. Thank you. Good question, Mike.
Sir,
Yes,
like you said that at the point where the concrete connects with steel, the stress is 125 psi, right? So at the top of the concrete, isn't the stress 660 psi? So the
where at in here?
Yes, at the top.
Yeah, it is 0.66 psi compression, but this one here is going to be 0.125 tension. Anything below this neutral axis is going to be tension. Start from 0.
So, sir, wouldn't the concrete fail at the top of the concrete? Like when the stress is applied at the top, it will fail.
In the top of the concrete? No, because this is here for the tension only. This limit is going to be for tension. Okay, let me draw this for you. Maybe it's going to be a little bit more clear. Here is the data when you do the stresses, right? And this is here is going to be the stress distribution. Let me draw it this way. Okay?
Yes.
And let me bring it this way. Let me zoom in. Anything above this neutral axis is giving compression.
Okay.
And concrete is good in compression. It can take all the way up to the 4,000 psi. We have no problem with this. The stress on the top, as you see here, is going to be 0.66 psi. So this is less than 4 psi. Then we should be good for this little triangle. Now let's look here below this neutral axis. Anything below the neutral axis is going to be in tension. Concrete is not that good in tension, and it's going to crack at this limit. It's going to crack. This is going to be the cracking stress as given by the ACI, the 474 psi. So concrete here is not good. Someone's going to say, let's just ignore this piece of the concrete because it's going to be under tension. So say, fine, if you're doing design problem, yes, you can ignore it. But if you like to do some research or you'd like to do some detailed analysis for this little, I'm going to say this piece of the section, of the concrete section, you see here, let me compare here the maximum stress in the concrete and compare it with the stress at which the concrete is going to be cracking. So when I find out the stress at the interface between the steel and concrete was equal to 125 psi, right? From here. I compare it here with the limit. What is this limit? This is going to be the stress at which concrete is going to start to crack according to the ACI. And this level here of stress was lower than the limit. It means concrete here is not cracking. So this only applies when you have the section tension. It doesn't apply if the concrete is getting compression. So this limit applies to this little triangle, but doesn't apply to this guy here, to the compression side. Okay?
And sir, where did you get the value of 1530?
1530, this number?
Yes, sir.
Very good question. Thank you, Mahim, for asking this. It's right here. This is going to be the moment of inertia. Moment of inertia of the section, after I was able to find out the centroid, right? We did here the centroid location, turned to be at 4.2 inches from the top, which means 0.8 inches from the top of the steel beam. After this, we did the moment of inertia for the section, considering that this section now is made out of steel.
Okay.
So this is usually covered in the strength of materials and statics, the first statics. But if you like, I just take some time to study this example. This example is going to be very good because it shows you here how do you find out the centroid of the section, and then how do you find out the moment of inertia. Like good solved example for you to remind you with what you have studied in the past.
Okay.
So take your time and study this in details. And my opinion here, my advice, that is just piece of paper and a pen or a pencil and redo this example again, this section of it. How do you find out the centroid? And then after this, how do you find out the moment of inertia? It's going to be a very good exercise for you.
Okay.
And let me know if you find out numbers that's different from these numbers that you're looking here at.
Professor,
Okay.
question.
Yes, sir.
You are saying because the neutral axis, from like neutral axis to the top of steel is like a little minimal distance, we can ignore it, but in y sub t or y sub b, we kind of still considering that distance to like distance of the in the steel. So are we ignoring it, or are we consider like assuming it's steel?
Okay. You have here two options. It depends on the problem and the purpose of it. If you are doing a design, like design case, if you have a design case, you ignore it. You ignore any concrete intention. If you are doing detailed analysis and research, you should not ignore it. You would consider it. So it depends on the case, right? What is the purpose of doing this analysis? Now you're going to tell me, I don't know. So I'm going to tell you simply, in each problem, I'm going to be very careful to tell you exactly what's the purpose of doing this. Right? So if I'd like to bring this for you in an exam or a quiz, I'm going to say, ignore the concrete intention, or I can say, this is during the design of a steel beam, so you understand what is the situation.
Okay, makes sense.
Yeah.
Thank you.
So in design questions, we'll ignore the concrete. And in
design,
analysis,
ignore the concrete intention.
And in analysis question, we will incorporate the concrete intention.
Yes, you'll include this and just leave it like this. And then you be sure here that the stress, like the tensile stress in the concrete, tension, it's not going beyond this limit, the 7.5 square root of F prime C.
Professor, if the tension goes beyond 474, would it be a problem?
Yeah, you cannot, then you're going to ignore it. You cannot consider any concrete to be in tension more than this value in detailed analysis.
But it still will add some capacity, right? Like it still has a capacity.
If it is more than 474, it doesn't have any capacity. It doesn't have any values.
Okay.
If it is less than 474, it's gonna be okay.
Okay.
This is in tension again, not in compression, right?
Yeah.
Okay, good. So we said, okay, same problem here. We said this area here now is giving tension and I'd like to ignore it. I'd like to take this out of my analysis. So I say, okay, but when I do my analysis here to find out the neutral axis, how can I find out the neutral axis? If this area here doesn't exist, because at the beginning when I did the neutral axis, I'm gonna go back here a few slides. When I did my analysis here, I considered that this concrete to be completely solid. That's why when I did the cross-section area, I said 1088 times 5. So this here, considering that the entire area is solid, it's gonna be taking some stresses, whether it's gonna be tension or compression. Now, if you're gonna be disregarding this, the question is, what depth would you consider? Is it gonna be 4.2? Answer is no. Actually, this is gonna be an unknown. It's gonna be one of the unknowns. So I'm gonna show you exactly what's gonna happen. This distance here is gonna be called y bar, is gonna be an unknown. You don't have it. And this total area is gonna be equal to 1088 times y bar. And when you take the moment about the top of the section, so the area for this, the concrete only, considered to be a steel element, area element, is gonna be equal to 1088 times y times 1/2 of y. Y 1/2 of y is gonna be the distance from top of the concrete to the centroid of this concrete section. So this here is gonna be equal to 1/2 of y. This is why when you look here at this equation, it says y bar equals summation of a times y above the top of the concrete. It's gonna be 544. Someone's gonna say, where does this 544 come from? Actually, this is equals to 1088 times y bar, which means the area of the concrete transferred into steel, multiplied by y over 2. So it's gonna be 1088 divided by 2 is gonna be 544 times y squared. Location of the steel beam is gonna be the same. You cannot change it. It's true that this now instead of 5 inches becomes something lower, but the steel beam location is gonna be the same. This is why it says here 137.3. This is equal to the area AS here multiplied by 5 plus 15.9 divided by 2, which means this here is not gonna change from the previous analysis that we have done. Let me take you back. This analysis here. You see this 136, A times Y. This is not changing. I don't know, they changed a little bit. Oh, 137.3, excuse me. 137.3 is gonna be for the steel beam moment. So let me see here what happened. It's still as 137.3. Now, this here, this total moment of each one of the sub areas, you're going to divide by the total area. Total area of the steel is going to be 10.6. Total area of the concrete transferred into steel area element is going to be equal to 10.88 times y bar. Now, you're going to have this equation in y bar. It's going to be from the second degree. You can solve it. You're going to have two answers, and certainly one of them is going to be something that makes sense. The other one is going to be like a measured number that will never happen. So you take here now the depth for the concrete or neutral axis is going to be 4.14 instead of 4.2. Not big difference, but this just to go in this assumption here, ignore the concrete intention and find out now the new depth. It's okay. Now how about the moment of inertia? Moment of inertia for the section now, I guess there's some way of doing it, which is very similar to what we have done here. This is going to be the moment of inertia. And instead of 1530 is going to drop down a little bit because this little area of the concrete section that was ignored is going to reduce the total moment of inertia. And instead of 1530, now this becomes 1528. This can be also very minor change, but if you like to ignore the concrete in tension, this is what you need to do. It's not worth it. In my opinion, it's not worth it. Now here's again another round of analysis to find out the stresses. Bottom of a steel didn't change much. Top of a steel, it was exactly 0.998. Now it becomes 1.08. It's the same thing engineering wise. It doesn't make any difference. Top of the concrete is going to be 0.65, which also there's no big difference here in the analysis. So conclusion out of this example, there is a way of determining the stresses when you have this elastic distribution of the stresses to find out the stress at any location within the beam depth, including the concrete section above it. And in some cases, you may have the neutral axis through the concrete, and at that point, we can have this discussion. Should we ignore this section of the concrete or this part of the concrete to be in tension, or we should just consider it as long as this maximum stress in the concrete is going to be within the cracking stress? There's going to be a little discussion here. But yeah, here's the method. You should be able to figure out the stresses, and based on this stress, you should be able to find out whether this section is still in good shape or now it is failing. I understand that usually the steel section is going to be able to take up to 50 KSI for the yield point. Now, if you're doing elastic analysis, the question to you is going to be what stress value that you're going to be okay with. When the yield point is going to be at 50 KSI, are you okay with the stress, actual stress on the section to be 21.1 KSI or not? What stress level would you accept? Same thing in the compression. The concrete is taken up to 4,000 PSI. Are you okay with it to be 651 PSI? Let's give you very low. Look at this here. 0.65 compared to 4 KSI. 21 compared to 50, which means that you still have some room to add a little bit of more moment above this, if you like. Usually, this method is not really used for design. It is mainly used for stress analysis that you'd like to find out for an existing situation. You'd like to find out the stresses and do kind of evaluation for the steel beam. So if you have an existing steel beam with some concrete topping like this, and you wanted to find out the stress within the entire steel beam at different sections, because in some cases you do a check based on the plastic distribution. Now someone's going to say, what plastic distribution? I'm going to say like this that we have discussed, like in here, like the standard design case. And after you do this analysis, you don't like the results. Now you can go back and do actual stress analysis within the beam and see if your beam is going to be in a good shape, or this is no, I don't like it this way. So basically, the elastic stress analysis is used in a case like this. But I don't want you also to remember what the code says. The code says if you have a compact section, you can use a plastic analysis. If you have non-compact section, you cannot use a plastic analysis. You're going to be forced to use the elastic analysis. Where in code does it say that? I'm going to go back here. I'm going to say, look at this. When can you use a plastic stress distribution, and when can you use the plastic stress distribution? The plastic is going to be used if you have compact section. What's the definition here of the compact section? When H divided by TW is going to be less than this number. Once you go above this number, you have to use the elastic stress analysis. If you are going to be picking a beam to use for composite, usually your beam is going to be satisfying this requirement. It's going to be a kind of section. This compact section. So, all right, let's move forward here and do the plastic stress distribution. So I'm going to be going here to slide number 31 for plastic stress distribution. Now in plastic stress distribution, I'm going to be taking you here to case C. We have 3 cases. I'm going to just start by doing this. if this is going to be the plastic stress or the plastic neutral axis, amount of compression here is going to be the same as the amount of tension. The steel is going to be under F sub y, whether it's going to be tension or compression. You cannot change this fact. So the steel itself is going to be under F sub y. And any concrete on compression is going to be under 0.85 F prime C. Now what you're doing here, you're setting the compression to be equal to the tension so that you find out the location of the plastic neutral axis. So here in the plastic distribution, it's going to be completely different from the elastic distribution. In elastic distribution, as I've done here, you find out the centroid based on the amount of area, and then you find out the amount of inertia, and then you say, right at the neutral axis, you're going to have a stress of 0. You go up, it's going to be compression. You go down, it's going to be in tension. Okay, this is clear. This is going to be elastic analysis. In plastic analysis, finding the plastic neutral axis is going to be based on setting compression equal to tension. Now, I may have 3 cases. If I have bigger value of the tension steel force when I compare to the compression in the concrete, let's say, how about here? Let's say at the beginning, I don't know the exact location of the plastic neutral axis. So I'm going to say, let's say the compression of the concrete. Someone's going to say, how do you find out the compression of the concrete? Simply take 0.85 F prime C, now it's going to be compression, multiplied by the concrete thickness, multiplied by the beam width, by the beam flange width, which means the concrete width. We're going to have here good compression force. It's going to be going to this flange. At the same time, you assume that the entire steel beam is going to be in tension. So what you need to do, you take F sub y times AS. Now you look at the 2 numbers. If they're exactly equal to each other, which may not happen, it's going to be very rare, it means the plastic neutral axis happen right at the interface. Most likely, your beam is not going to show this. But if this is going to be one of the cases, the plastic neutral axis is going to be right at the interface. Why? Because compression here is going to be equal to the tension here. Now, my question is, if you have lots of compression in the concrete, let's say 1,000, and the tension steel is going to be only 600 kips. Now, where do you think neutral axis is going to happen? Is it going to happen in the concrete flange, or is it going to happen in the steel?
Concrete.
The steel.
In the concrete. Okay, I'll let you guys. Who said the concrete? Who said the steel? I want you to defend your opinion or discuss it further.
Concrete.
I said here, if the concrete compression, if I take here T times B times 0.85 F prime C becomes like 1,000. And then I took here AS times F sub Y, it is equal to 600 kips. Means if the entire section of concrete exposed to compression and you compare it with the entire section exposed to tension, you're going to have here lots of forces. But in reality, I know that the compression needs to be equal to the tension. So I'm going to say, no way that the compression of the concrete is going to be approaching 1,000. Why? Because the maximum steel tension force that you're looking here at is going to be only 600 kips. Can you have more tension than 600 kips? Say no, because I took everything here that's able to take tension multiplied by F sub Y. And it gives me here 600 kips. So I said, okay, you have maximum tension of 600 kips because the steel cannot take more than 600 kips. And the steel is going to be the only element that's going to be able here to take tension. Now look at the compression. You need to say now, what is the maximum compression force that the concrete is going to be able to see? I'm going to say, you know what? Usually C is going to be equal to T at the end of the day. So it is true that the concrete, it is showing based on your simple analysis, 0.85 F prime C times B times T is going to be equal to 1,000 kips. But in reality, it cannot be more than this 600. So what's gonna happen, we need to push this neutral axis up here and only take this section of the concrete. This section of the concrete, right? And say this section of the concrete, the compression in there is gonna be equal to the 600 kips. Now, do you know this compression block depth? You're gonna say, I don't have it. So I'm gonna say simply set C equals to T, very similar to what we have done in concrete design, and based on this, figure out the compression block depth A. So this depth here, we're gonna call it A. So this is gonna be the first case. First case, if the neutral axis happens right here, which means this total compression is gonna be equal to the total tension. Second case, you have lots of compression force in the flange, you have lower value in the steel. So in this case, I'm gonna say neutral axis is gonna happen right here. Okay, good, all right. Now what happened if the steel tension force is just big, like 1,000 kips? Now I'm changing here the rules, right? And the compression concrete turns to be 600 kips. Not now what compression the concrete? I'm gonna say compression the concrete for the entire section of the concrete. So this entire section, 0.85 F prime C times B times this T is equal to 600. And the maximum steel, when you take AS times Fy, is equal to 1,000. So let me put the numbers. Now here is going to be equal to 600 kips. And the steel can take a tension up to 1,000 kip. Now where's the neutral axis going to happen? You're going to say,
Steel.
no, concrete. Yeah, go ahead, please, Andrews.
It's gonna be towards steel because
Steel, this is correct. And why is that? Because the maximum tension or compression is going to be 600 kips. You cannot go beyond this, right?
yes.
So you need to push this down so that you have here a little bit more compression on the concrete and a little bit of the steel to be equal to that side. So, okay, it means I'm going to have a case like this or a case like this in that case. So this case here is going to happen if you have the compression in the concrete to be less than the total tension in the steel based on AS total. So, okay, fine. Now let's see what's written here. It says here compressive force is going to be the smallest of. I'm going to start with this one here, item number 2, 0.85 F prime C times AC. I understand, yes, because it's going to be either 600 or maybe in the first assumption that I start with, maybe it's going to be 1,000, but it will not go above the maximum tension force, which is AS times Fy. So I'm going to say, yeah, this 2 makes sense to me. It's exactly what I have discussed right here. It's going to be the smallest of. Either it's going to be AS times Fy, like in the first case, when this equals to 600, and the compression of the concrete was equal to 1,000 kip, or like this numbers, or this case, what I'm showing here is going to be the lowest of 600 versus 1,000. In this case, I'm going to be taking here the 600 kips. I said, okay. And then it says here, summation of Qn. What is this Qn? Something that we didn't talk about. If you have here 600 kips and you have here 1,000 kip, like this numbers that you're looking at, which means that you have compression C and then you have tension T, and you're going to be taking the smaller of the 2 to be the actual number to be used. You need to be able to connect between the concrete and steel to be able to transfer this force from the concrete to steel or steel to concrete. Because you just say C is going to be equal to T, right? So how can you confirm this is going to be equal to each other? I mean, what is a mechanism to transfer this compression from one side to be tension on the other side? Because it says it's going to be equal to each other. You say you need to have here enough studs, mechanical connectors. If you'd like to remember what is a mechanical connector, I'm going to take you back here to this Nilsson studs, the mechanical connectors, these connectors here that we have watched this video for it. I'm talking about this connection here. this connection between the concrete to steel. This Nelson studs, in this case, they're going to be seeing this force, whether it's going to be tension or compression, like compression the concrete or tension the steel. If you need to transfer to the other side of the section, it's going to be moving from the steel section to the concrete as in shear in the mechanical connectors. So this mechanical connector is not going to be seeing tension force, and instead is going to be seeing shear force. So let's assume here for a second that you didn't put any Nelson studs. Can I say that I have a composite section? You're going to say no, because there is no connection between the concrete to the steel. If I put plenty of these studs, you're going to say, well, maximum compression or tension is going to be controlled by the amount of Nelson studs or mechanical connectors that you're going to put in there. So if you have enough connectors to transfer compression or tension force from one side to the other side, it means that you have full composite action. So let me move here to my section in the analysis. Total shear strength for the stud that you added there is going to be equal to summation of Qn. Qn is going to be the shear strength of one stud. So if you like to get here the full composite action of the beam, you need to provide enough studs to be able to take this force. Either it's going to be the smaller of the two, AS times Fy, or 0.5 A prime C times AC. It's going to be compression the concrete or tension the steel. So you need to have enough Nelson studs connecting between the concrete to the steel. Otherwise, you cannot have this full composite action. So the question is, if I added 50% of the Nelson studs needed between the concrete to the steel, what's going to happen? I'm going to say now the compression in the concrete, it is going to be 50% what you have considered if you would have full composite action. I don't know if this makes sense or not. But let's say for now, usually you're going to put enough studs so that you're able here to transfer the compression from one side to be tension the other side.
Professor?
Yes.
If we, for example, if we only provide 50% of the stuff, then the failure can happen at the stuff or not?
So what's the question?
So for example, if we only provide 50% of the stuff.
Yes.
So if there any chance the failure happen at the stuff or not? So
okay.
when the fork will not fully transfer to the steel.
Okay. So let's say that we didn't put enough Nelson studs. We put only 50%, right? So what's going to happen to the shear strength of the studs? So let's say if, according to this example, this numerical example that I threw there, if I put here enough Nelson studs to take 600 kips as in shear. Now you look here at this beam, and then you say, now I have a compression of 600, tension of 1,000. I added Nelson studs to take 600 kips. Now what is the compression force in the concrete or in the section? You're going to say the minimum of AS times Fy, which means 1,000. 0.85 F prime C times AC, 600 kips, and 600 kips for the shear strength. Now, someone here is going to come, like what you're saying, and provide Nelson studs is going to be transferring only 300 kips. So in this case, we're going to say compression force is going to be the smallest of. Run the same numbers again. It's going to be 600 kips versus 1,000 versus 300 kips. Now, my compression force is going to be equal to 300 kips, which means now the Nelson stud that you provide there is going to be controlling how much composite action you'd like to get out of this combination. This combination of what? Of having concrete, steel, and Nelson studs. So it's not just about the concrete, not just about the steel, it's also about connecting them to each other. And here's what happened. If you didn't put any Nelson studs, you don't have composite beam. So the whole thing here doesn't apply. You cannot do it if you didn't put any Nelson studs. And in this case, summation of Qn is going to be equal to 0. So compression force in the composite action here is going to be equal to 0. Therefore, you don't have a composite beam. Generally speaking, I'm going to assume here, if I have situation like this, I'm going to have full composite action. Usually, I'm going to say I have full composite action in the examples. I need to specify exactly how much composite action. If I said that we have full composite action, you don't do any analysis here in this. You just take the final compression force and then you determine the number of studs needed to provide you the full composite action. We're going to be going through this. Okay, an example. In this example here, it says that you have composite beam consists of W16 by 36, A992. This is going to be grade 50 KSI. You have 5-inch thick concrete slab, 87-inch wide on the top. The strength of the concrete is 4 KSI. It says here, compute the available strength of the composite beam. Available strength, it means flexure strength, which means Phi-man. Assume that sufficient stud anchors are provided for full composite behavior. I said, okay, good. If I have this assumption, it means when you pick here the compression force to be the smallest of the three, you don't really need to do this check. You don't need it. And no one here is asking you to find out number of studs. You just say, assume that you have enough or sufficient studs. So do not do this check. Just check the concrete versus the steel. Does this make sense? Yes? No?
Yes. Yes.
All right, good. Here's AS times Fy. Where'd you get this AS from? 10.6 cross-section area of the steel beam, W16 by 36. 50 KSI. Here's the tension in the steel. I say now, how about the concrete? Concrete, yeah, 0.85 F prime C times the cross-section area of the concrete. 0.85 F prime C as given here, 4 KSI. And the concrete is going to be 5-inch by 87. Now we have 1479 kips. I have a question here for you before I continue. Should we divide this by N, the modular ratio, or I should not? Someone's going to say, what N? I'm going to say modular ratio that we did when we have the elastic stress distribution.
No,
If it's
because
zone, right?
No, but I'd like to hear from you. Go ahead.
because we consider the full section of concrete that has this stress
Yeah,
distributed.
because this section, the top piece of which is the flange, is going to be concrete. And there is no need here for us to make it as a steel section. We are not interested in finding out the moment of inertia, right? We are not doing elastic stress analysis. This here plastic. So we're doing here strength analysis, not stress analysis. I said, okay, now I have two numbers. The steel is going to be 530, and the concrete is really thick and wide, and I have enough strength. Now, where do you think the neutral axis is going to happen? The plastic neutral axis is going to happen in the concrete above the steel, or is going to happen within the steel section itself?
In the concrete.
Probably in the concrete
It's
section.
going to happen in the concrete. Absolutely, this is correct. Now, the steel here is controlling, therefore the compression, the section is going to be equal to the smaller of this two. Now this is here gone. The studs are gone. I don't really need to do it because it says assume that you have enough anchors. So we can say now I have compression force of 530 kips. This can be very similar to what we do in concrete design. In a simple concrete design, this is exactly what we do. Look what happened here. We're going to say here's the compression force, 0.85 A prime C A B. This is exactly what we have done in concrete design. And the tension force is going to be equal to what? 530 kips, because it's going to be tension equals to compression. Now, say, do you remember this equation in concrete design? You set compression in the concrete is going to be equal to the tension in the steel, A is going to be equals to the tension. It says here the C because equal to T, the 530 kips, divided by 0.85, divided by 4 KSI, divided by 87, which means the flange width. Now you got this A, compression block depth. It's exactly what we do in concrete design. Their compression block depth here is equal to 1792. Now, how much is the distance from tension to compression? It's going to be the other question, right? Now, where's the tension force? Tension force is going to be right in the mid-height of the steel beam at D/2 from each side, like the center. Very similar to that case in concrete design when we say tension is going to be right at the center of the rebars. Am I correct? You guys remember this? Tension is going to be right at the center of the rebar. Now, tension is going to be at the center of the steel section. Here's the tension. It's going to be at D/2 from each side. And the compression is going to be in the middle of the concrete block depth. It's going to be at A/2 from the top. Now, how much is the distance between tension to compression? You say it's going to be equal to D/2 plus the thickness, the 5-inch, subtracting A/2. So again, it's going to be equal to what? D/2 plus the slab thickness from here to there, subtracting A/2, which means this little bit or this little bit. Okay, let me see this analysis. It says here y equals D/2 plus T, the 5-inch, minus A/2. Here it is. 15.9 was the total depth of the steel beam. You divide this by 2, here's D/2. You add 5-inch, you go to the top of the section. You subtract A/2, you have 12.05. So what's next? I'm looking here for the moment. Moment's gonna be either tension or compression times this y. And this gonna be the nominal moment capacity. Here's Mn. It's gonna be equal to C times y or tension times y. I say, okay, they are equal to each other. It's gonna be 530 kips multiplied by 12.05, which is this y distance that I just calculated out. It's gonna be this number as in kip inch. Divide this by 12. Now it's gonna be in kip foot. The phi factor is 0.9. So multiply this by 0.9 times 532. It's gonna be 479 kip foot. This is now the phi Mn, which means the moment capacity of the section, of this composite section, provided that you have what? That you have full composite action. Now a question to you. If I don't have any concrete slab action on the top, which means no composite action, what moment capacity would I end up with? So I want one of you guys, open the steel book, look for this steel section here, W16 by 36. Would you please find me the Z value for it? I need someone here to go for W16 by 36 and get me the Z value for it.
The ZX value is going to be 64 inch cube.
64?
Yes, 64 inch cube.
Z is going to be inches of 4. ZX.
No, it's inch cubes, Professor.
ZX, I'm sorry, yeah, section modulus. It's not moment of inertia. My apology. What number exactly?
64.0.
64. All right, I'm going to say Mn. How much is Mn in this case? 3200. 3200 what? Kip inch. Can I do it in kip foot? Phi Mn. What's wrong? Phi Mn. Here is Phi Mn as in kip foot. $240. The composite action, how much would you get? $319. Wow. See how much increase? 33%. Yeah, I have increased in the trends of this beam by 33%. Just by adding these connectors between the concrete and between the steel. Which means if you missed this in your design and you did not put enough Nilsson studs, what's going to happen? You're going to end up with Feynman of 240 kfoot, right? If you're doing here, ultimate design is going to be 479. So let me put this as 479. Look at the change. Can you guys please confirm that W16 by 36 has ZX of 64? Are you sure? Just someone else confirm it, please. 16 by 36?
Yeah, I'm seeing 6.
Yes, sir, it's
34.
I'm getting
64.0.
64.
Correct.
Okay. So if the beam is fully braced in the top, you're going to end up here with 240 kfoot. If you do here LR of D, you have it at 479, and you have 100% additional fracture strength. I guess worth to be used, right? You cannot really ignore it. This is a lot. Any questions before I move further?
So do we use LRFD and ASD and we take whichever number is lower?
No, usually you just do the LRD. Don't do the ASD in this course. But this is here because I'm taking this from the book. I'm just leaving in both cases so that you know the difference between LRFD and ASD. Come to analysis. The difference is that, as you see here, after you do the MN, either that you multiply by 0.9 or divide by omega for the bending, which in this case is going to be 1.67 for bending. But
Okay,
now the
thank
load
you.
factor is going to be different because if you have dead load and live load, here you just add the dead load and live load and you call it moment. Here you're going to multiply by the load factors, the 1.4 versus 1.2 plus 1.6, right? Then you take the larger, compare it with this value here. So here you're going to have in the demand, you have load factors. Here there is no load factors. It's just dead load plus live load.
Okay, yeah, that makes sense. Thank you.
Okay, thank you. Bottom line and conclusion of this, composite is, I mean, effect is great, should not be ignored. If you have a chance here, once you have some concrete slab, try to use the full composite if you can, based on, let's say, providing the minimum number of studs. Because the question here, if the full composite means that I'm gonna put here a stud at 4" on center, but I don't really need all of that. Let's say my mom demand, I'm gonna throw here some numbers. My mom demand is equal to 320 kfoot. Okay, this is gonna be M sub U. The capacity here, if I have full composite, is gonna be 320. And the capacity, if I don't consider any composite, like if I still consider here the bare steel beam, I'm gonna say phi Mn is gonna be equal to 240 kfoot. What's gonna be the best option here available? What would you do? Would you do full composite and throw a Nilsson stud at 4" on center? Let me see, what does it mean? My demand, if no Nilsson studs at all, is gonna be 240, and my beam is not gonna be good, right? Because the mom demand here is equal to 320 kfoot. So my beam is not good. If I provide here a Nilsson stud at 4" on center, I'm gonna have a capacity of 479. Do I need all of that? Now compare the demand with 320. I don't need all of that. Why would you take the beam of 240, you add the studs at 4" on center and bring it to 479? Why don't you go, let's say, to an option of, let's say, putting, I'm just throwing here an assumption, maybe put a Nilsson stud at 12" on center and end up with moment capacity of, let's say, 360 kfoot. Would that be okay with you? So here's an option. I'm just throwing here an option. I don't know the exact number. I'm just throwing it for sake of discussion. I'm gonna say, let's put here stud. So I'm gonna say a stud at let's say 12 inch on center. And for that, I'm gonna have here Vmn of 360 kfoot. What do you guys think? Is this gonna be a better option, or should we go with Nelson stud at 4 inches and get up to 479 foot? Which option would you go with?
12 inch on center.
Yeah, I would reduce it. So this number here, the 479, is based, I'm just here throwing an assumption for sake of discussion, based on stud at 12 inch, 4 inch on center. So this number here is good, but you're going to be throwing lots of studs. This number is still good. You have good margin here of safety, 360 versus 320, and you're not putting as many studs. And you know studs are going to be taking some time. Of course, it has some cost. And from time to time, you're going to have a bad stud. So in this case, you need to take it out and put another good one. Maybe 3-4 inches away from it. So definitely, I'm going to go here with this option. This is going to be the preferred option in this case. So instead of going at 4 inches, I'm just going to go here at 6 inches, at 12 inches, as long as I have here enough capacity, the 360 to cover the demand at 320. All right, we are done for today. Please go ahead and sign out. Type your name and leave. If you have questions, stay around.
Will you be uploading the solutions for the homework soon?
Is that the solution? Yeah, certain sections are going to be uploading it. Not all the homework, but certain homework, I'm going to be uploading it.
Okay, thank you.
No problem.
Professor, I was wondering, for homework 1, did you already grade the assignment?
Yeah, it should be posted already.
For some reason, I have a 0 out of 10 for it.
So I have not received, yeah, if you like. So in this case, I have not received your solution. It's not posted there. You can double check it for you.
Thank you, Professor. See you Wednesday.
All right, see ya.
Professor, will you be uploading the lecture videos from last week?
Yeah, I uploaded, I guess, yesterday or today. It should be there.
Okay, just making sure. Thank you.
Yeah.
Professor, where are you uploading the lecture videos?
When did I upload it?
No, where? Are you uploading them on
Oh, where?
Canvas?
Okay, hold on. Let me show you how to find it.
Okay.
Yeah, give me a second. This is what you see, right? And then you go in the lectures. You see in the lectures? You see
Yeah.
the lectures on YouTube?
Yes.
Click on it. And then don't click here. You click on this one. Look at this.
Okay.
And now you have them all.
Okay. Thank you, Professor.
No problem. No problem. Any other questions? And
No.
Michael, stay with me, Michael.
Yeah, I'm here, Professor.
Yeah, stay. Don't log out. Stay with me.
Okay.
Professor, I have one request. I didn't check the homework for this time, and I wasn't able to do it. Could you